how about sort of outside the United States, maybe even outside of the sort of the larger, most developed economies? How do you think AI is going to affect the world more generally?
I feel like I hope that AI will have a very large democratizing effect. Because one of the most expensive things in today's world is intelligence. It costs a lot to get a highly skilled specialist doctor or to tell you what's going on, or costs a lot to get a highly skilled tutor to mentor your child one-on-one. And AI, and then whereas I don't see a path to making human intelligence cheap, it just costs a lot to train a skilled human being, there is a path to making artificial intelligence cheap. And what this means is, today, only the relatively wealthy can hire certain types of staff to do certain types of things for them. But in the future, I would love a very single person can have an army of smart, well-informed staff to do all sorts of things for us. And I think this would...
Their health advisor, their tutor, that kind of thing.
Yeah, yes. And I think that giving everyone an army of staff to help them that today is available only to the relatively wealthy, this will lift up a lot of people.
Andrew, welcome. It's so glad to have you back.
No, always great to see you, Astro.
Awesome. We're going to talk about a lot of different things, but I want to start with something that I remember fondly. We were in graduate school at kind of roughly the same time, and when we were talking to you about starting something at X that later got called Google Brain, you had done something really kind of unusual and memorable for your graduate thesis. Can you tell the audience kind of what your graduate thesis was, both kind of what was technically interesting at a very, very high level, but also like what you made happen?
For my PhD thesis at Berkeley, I built a little neural network that flew a helicopter. And I guess it was unusual at the time because reinforcement learning, which is hot now, it wasn't hot back then. But I wound up asking some friends to let me use a helicopter and then, trained a little neural network with a little algorithm that we invented to keep it hovering in the air. And it stayed rock solid. So you could watch a video of it and you go, is this a video? You look at the picture. And I thought that was cool. That actually got reinforcement learning a lot more attention than it was getting at the time. And it was fun to fly helicopters.
Exactly. That's... People listening to this now might not remember, because now that they see all these vertical takeoff and landing kinds of craft, they think that something that's rock steady in the air is pretty easy. But back then, something that learned how to do that kind of like was a bit of a kick in the head in an exciting way to the field, I remember.
It was fun. I think I've been fortunate for a lot of things I do to go off the beaten path and do something weird. And sometimes it doesn't work out. That's part of what happens when you go off the beaten path. But when it works, I think the helicopter result got a lot of attention and moved reinforcement learning forward at the time.
Yeah. I remember as we were talking from the X perspective about starting something sort of like what ultimately became Google Brain here at X and later at Google that you co-founded, I remember, and you brought this piece of history, what you had written when you were at Stanford as a young professor about what you thought we should, or Stanford, later X, should do. My memory, not having skimmed this yet, I'm very curious to go look at it, is that there were two things that I think was your thesis, though I remember that myself and Sebastian, my co-founder, co-director of X at the time, very much bought into. One of them was that scale matters, that Jan LeCun and others had sort of showed this academically, but that no one had actually managed to deliver scale. And so it wasn't proved yet, even though everyone strongly suspected it.
I would say at that time, people hadn't proved it academically. And in fact, I remember going to NeurIPS, at that time, the NIPS NeurIPS conference, and I was talking to people saying, got to scale up deep learning algorithms. And I was getting advice from very senior people saying, hey, Andrew, why are you trying to build bigger neural networks? Like, go invent new algorithms. So it was actually
2011.
Yeah, I remember pitching Google Brain, what became Google Brain, to Larry Page in 2010, but it was around 2008. So I was going around academic conferences, and then at that time, scale was actually controversial. People did not believe in it. And well-meaning, very senior people, I remember Yosha Benjo saying, "Hey, Andrew, this is not good for your career."
That's very ironic in retrospect, given not only how right you were, but how good for your career in particular it's been. The other theory that I remembered, correct me if I'm wrong, that I felt like was part of your thesis was that in the human brain and in other brains, a lot of different signals, the signals from our nose, the signal from our eyes, the signal from our ears, even from our taste buds, goes through similar parts of our brain. And you were asking the question, maybe there's something useful about that, about forcing a system to be overloaded in that way, and that asking a system to do a lot of very different things might cause it to be less brittle, more intelligent. Am I remembering that correctly as a part of the thesis that you had at the time?
Yeah, it was kind of a two parts. It was really the one learning algorithm hypothesis. So I was inspired by these neural rewiring experiments, which show that things like if someone tragically has damage in part of the brain, other parts of the brain, the same physical brain tissue, could learn to see that was previously learning to hear. So it really made me wonder, and it wasn't the only one, it really made me wonder, do we need totally different software or algorithms for seeing and hearing and doing all these different things? Or is there one learning algorithm that, just depending on what data you give it, is it text or images or audio or something else, will learn to figure out how to deal with that data? In hindsight, I think this one learning algorithm hypothesis, it turned out, I think, to be much more right than wrong. But again, looking back, I think I overemphasize looking to neuroscience for inspiration. And so the specifics from neuroscience mostly turned out not to be helpful. But this high-level idea that maybe the human brain has one algorithm that does a lot of stuff. So we should try to get a computer to have one algorithm rather than having 10,000 people invent 1,000 algorithms. Maybe you can have a small team invent one algorithm and just feed it very different data. And that really worked out.
Right, which at the time was heresy, but is now what everyone is doing.
Yes, I actually remember speaking at the National Science Foundation workshop where I was talking about one learning algorithm hypothesis. I was younger at the time, and I was kind of poking fun at computer vision people hand engineering. I remember one very senior computer vision researcher stood up in public and kind of yelled at me. And as a young professor, that was slightly traumatizing. But maybe years later, I can look back on it and smile and say, it actually worked out okay.
Yeah, and people who are changing a field, as you did, generally do get yelled at along the way. So, as you were coming into X, why, you had this vision, you could have tried it in different places and in different ways. Why come to X? Like, what was your memory of choosing to come to X with this idea, your initial experiences with me, with Sebastian, with Larry and Sergey?
Yeah, so I remember at the time, Sebastian Thun, who was running X together for you at the time, Sebastian Thun deserves much more credit for the starting of Google Brain than I think he's received so far, candidly. Sebastian and I had offices at Stanford right next to each other, so we shared the wall. If I banged on my wall, he would hear it on the other side. And so my students at Stanford, Adam Coase and others, had demonstrated that the bigger we build a neural network, or bigger we build these learning systems, the better it perform. And so I felt like I had this, secret data. It wasn't secret. I talked about it, but people just didn't believe me, which maybe was a positive thing. I don't know. With this data showing that the bigger we build neural networks, the better they perform. And so I was talking to people saying we should scale up these algorithms. And Sebastian points out to me, Google has a lot of computers. Why don't you pitch Google to let me use Google's massive compute infrastructure to build much bigger neural networks than anyone else had built? So Sebastian set up a meeting for me to pitch to Larry Page. And I remember I prepared slides on my laptop, came all prepared with slides. but we're eating in a Japanese restaurant, so it was inconvenient to pull out my laptop. So I wound up just talking to Larry with Sebastian there as well. And fortunately, Larry happened to buy into whatever I was telling him, and then authorized letting me work with Sebastian and you and X to take forward the project that later became Google Brain. So I think that I think that dinner, I still remember it clearly. It was a very high stakes conversation for me, and I'm really grateful to this day to Larry Page for buying on to what was a pretty crazy vision at the time.
Neural networks. By 2012, things had changed. People were starting to get pretty excited about neural networks. But even 2010, maybe 2010, neural networks were mostly still out of vogue and had been for a long time in the artificial intelligence world. What was your thinking? Look, scale is one thing. We can scale these things up, and scale may really matter. Separate question, what to scale up? Any thoughts on neural networks as a representation? That's now something that everyone just takes for granted as being sort of in the water. But as you remember back in 2008, neural networks was not what everyone was doing, and was not at all taken for granted that was what was going to be the breakthrough for artificial intelligence.
Yeah, neural networks have been out in the wilderness, kind of rejected by a lot of AI for a long time. In fact, looking back, it was difficult to publish neural network papers in the leading conferences, which is why a lot of my early work was published in workshops rather than in the main conference at the time. I think back then, a lot of the intellectual excitement, the way you get a paper published at the top conference was by doing really tricky mathematical work, have a really clever idea, maybe prove a theorem. That's how you get a research paper published, and you earn the respect of your peers with your very clever ideas. And then I showed up and said, you know what, let's get a lot of computers and make this much bigger. And that was viewed as, where's the intellectual rigor in that? You're just building stuff. Why do you want to do that? So I think it was a really controversial. And then frankly, I actually saw as scaling up deep learning started to really take off. I saw some of the people that frankly had spent 20 years of their career tweaking algorithms. It was actually emotionally wrenching for them because they spent decades of their career fiddling with these algorithms in very clever ways. And then a bunch of people like me, we said, you know what, let's build a really big computer, throw a lot of data at it. And when it started to outperform their, decades of intellectual work, it was tough. Many of them adapted and kept on continuing to do good work. But when the disruptive innovation that comes that obsoletes what someone's worked on for a long time, it sometimes takes a while to adjust. It turns out our first paper pushing to use GPUs to scale up neural networks, another controversial idea. We published that in a workshop because couldn't get accepted in the conference at the time. And now it's so obvious, that everyone knows you should use GPUs. I think one of the things that I was seeing back then was there was a small group of us, not just me, but also, at this CFA meeting in Canada where Jeff Hinton and others hang out as well. A few of us were generating data showing real momentum. A lot of times when there's disruptive innovation, it really doesn't compete with the incumbent technology. And at that time, the neural networks we're training, they were definitely worse than traditional computer vision algorithms, traditional text processing algorithms. But we knew we're onto something because while not yet competitive, it was rapidly getting better. And I think my students and I at Stanford saw that if only we could build bigger versions, then it would become competitive. And that was the bet we wanted to place.
And as a very young professor at Stanford, you were describing before how you got a lot of pushback at the idea that scale might really matter. What gave you the confidence in those early days to keep pushing for it when there were people who not only disagreed with you, but were angry at you for saying that this was the way forward?
I had secret data. Well, not really secret. We actually published it, but others didn't believe me, so it might as well have been secret. But my students, Adam Coase and Hong-Lek Lee, generated a chart where the horizontal axis was the size of the model, vertical axis was how it performed, and we tried a ton of different models, and for every single model we tried in that research, curves just went up and to the right. So I knew, based on data, that the bigger we could build the models, the better it would perform. And I think as a scientist or as an innovator, you don't get to do good work by just asking what everyone thinks and taking an average.
Well said.
It's fine to ask people what they think, but in the end, you have to have a hypothesis for what you believe in. And mine was shaped by data that we had generated at Stanford that we published, but somehow I struggled to get people to pay attention to this. So we actually had a long head start on scaling before other teams then jumped onto that too.
Once Google Brain was starting to get set up, Jeff Dean kind of ended up as your partner in crime in building out Google Brain. What was how did you two meet? How did that work out? How did you divide up the work?
I think I was really fortunate that Jeff Dean joined the project. I think when Sebastian Thun and I, under Larry Page's direction, were working to start the project, Larry asked me to speak with a lot of people in Google. And so I remember chatting with Jeff Dean, Greg Corrado, Tom Dean, Jay Yagnik, many, many others. And I remember pitching to Jeff this idea that if only we can build bigger neural networks, things would get better. And that was the idea that excited Jeff. And then as the project got going, all of us that were working on the project at the time knew that if we could get Jeff more and more involved, he would be a tremendous, value add.
Force multiplier for the team.
And so, I don't know if any of us ever told Jeff this, but we actually had some conversations, like Greg Corrado and I were chatting, all right, what do we do to make sure Jeff is excited and keep him engaged? And we're always wanting to make sure he was excited and we want to do more and more. And fortunately he did. I think as, when he became highly involved when we were partnering day to day, he wound up being the systems person. I mean, he built a lot of Google's infrastructure. He understands scaling at a very deep level. And I wound up being the machine learning person. And I think it was that partnership of me bringing the machine learning expertise and Jeff bringing the computer systems expertise that allowed us to use Google's infrastructure to scale up machine learning algorithms, and that started to deliver real results.
Yeah, it was an interesting analogy at the time. One of the things that Jeff had brought to Google into the world was taking a really hard problem, like looking at all of the potential search information in the world, finding what you're looking for and returning it within milliseconds, which means you have to split up the problem. And it turned out that splitting up of the problem and then recombining the results, which was central at the time to how Google solved its problems, turned out to be very similar to the training work that you all did as you were training larger and larger neural networks, right?
Yeah, so I think Jeff had invented this technology called MapReduce that takes work, splits it up, does it on lots of computers and brings it back together. That was version 1 of how we did some of the training. And then as we built more and more versions, which then eventually led to things like TensorFlow, I think the technology stack kept on evolving. I would say one thing that I think we were slower to do at Google was embrace GPUs, partly because Google has such a brilliant CPU compute infrastructure.
So let's dive into that for a second, because our commitment at X generally was that we would be mostly focused on things that had some hardware component. So in the early days, we were excited about Google Brain being at X, but it was partly because we imagined that there might need to be specialized hardware that would go with the specialized software, a brain to go with the mind, as it were. And then over time, you and the team were having so much success that, at least for a while, the interest in specialized hardware went away. But then later, Google Brain ended up starting the whole TPU process, though that was after it left X. Any memories about how we got to both temporarily not doing hardware and then later getting back to hardware?
Yeah, so I think Google Brain made a ton of great decisions. One that I wish we'd made differently even earlier was the GPU, maybe TPU decision. And I remember Jeff and I were actually speaking with a lot of the data center operators, building up the Google's launch clusters and so on. And there was a concern at the time, which is legitimate, that we started sticking a few GPUs here and there, it would create a very heterogeneous compute environment that became hard to use.
Can you unpack for people what a GPU is and what a TPU is, just so they recognize those terms?
Sure. So most computers powered by CPUs, computer processing units, and then GPUs are graphics processing units, originally designed for making computer graphics, but turned out to be fantastic for training very large AI systems, like large neural networks. And then TPUs, Google's invention, Google Brain team's invention, is Google's take on specialized hardware for training these very large
tensor processing.
Tensor processing units, right? And so I think we saw that GPUs were working well. And in fact, early on in Google Brain, we're working on speech recognition. And we actually had a GPU server, one, maybe two. I can still picture it sitting under someone's desk with a nest of wires feeding to it. And we actually saw with that one computer, I think we saw GPUs were helpful, but the concern from the Google data infrastructure point of view was Google has at that time had a compute infrastructure so someone could write code and have it run pretty seamlessly almost anywhere. But GPUs is a very different type of hardware, and so would change the work that programmers have to do to specialize it. And so we're looking at, boy, if we buy a lot of GPUs, can we use this also for YouTube transcoding? And is it good for anything other than training AI models? And I think because of those things, we stalled out a little bit and did not as aggressively pursue that here at Google as maybe I should have pushed harder for. I wound up actually doing demo stuff using GPUs at my Stanford group because that was a scrappy team that could a very messy infrastructure, and it was okay. But having said that, I think we got quite far with CPUs, and then as Brain started to move in more into GPUs a little bit later, and then building TPUs, clearly that worked out just fine.
It was after Google Brain had left X that the transformer was formally invented, that the paper was published. Did you see little bits of transformer or transformer-like work? Tell us about maybe some of the snags that you hit in the early days of Google Brain, and also some of the things that felt exploratory then but turned out to be really important.
The brilliant thing about the transformer paper was, and I think to this day only some people understand this, was the authors grew up in that Google Brain tradition of scale. And so a lot of decisions of how to architect the transformer network, it was all about designing a neural network that would scale well on GPUs. So a lot of things like the attention mechanism, which is a very clever way for a neural network to decide which parts of a sentence to pay attention to.
Can you explain to the audience what the transformer innovation was around attention?
So I think before the transformer paper, there used to be algorithms that, say we want to translate a sentence from English to French. You would read the whole sentence, try to memorize the whole sentence, and then try to regurgitate the French translation. And it kind of worked okay.
That's pretty hard.
Right, it was pretty hard. It's a long sentence. And the transformer paper had this innovative architecture that would keep the English sentence around. And then as you're trying to write the French sentence, depending on where in the sentence you are in generating the output, you could pay attention to the specific part of the English sentence you're translating. And it turned out that this required a lot of computation to be able to look at the entire sentence in English and the entire sentence in French and figure out what to look at when you're doing what. But because it scaled really well on parallel hardware, GPUs and TPUs, it worked really well. And this later became, as we all know, the foundation for modern foundation models, where instead of translating from English to French, we quote translate from a user prompt to the answer to whatever the user is asking. And a large part of why the transformer paper worked so brilliantly and got so much traction was because the authors designed the neural network architecture very cleverly to make sure that every single step was highly parallelizable and could run well on the GPU. And so that gave it a fantastic compute substrate to train it on tons of data, and that made it work really well.
In the early days, Google Brain, when it was still at X, you could have worked on anything. You could have worked on translation. You could have worked on turning speech into text or image recognition. How did you pick a few things to focus on? And did you throw some away because they weren't working as well or because they would be less commercially useful?
So, in one of the first things I worked on when I started at X was actually teach a class within Google on neural networks. I think Tom Dean and Greg Corrado and I worked closely on this, if I remember correctly. But it turned out to be a great, I think something like just shy of 100 people came. But we were meeting every week, sharing my weird ideas about neural networks and scale and what we're doing at Google Brain. And then fortunately, this helped us make many friends and find many allies across Google. And so one of the first teams we wound up working with was a speech team. For two reasons. First, we felt that there was a lot of potential in scale to improve speech.
By speech, you mean listening to the audio of speech and figuring out the words that they're saying so you could literally write down the text that comes from that audio.
Yes, speech recognition, right. At that time, I think voice search wasn't yet as mature as it is today, but the idea that you can talk to your mobile app and use your voice to search in Google, that was really exciting. So we want to improve the accuracy of speech transcription. But I think at that time, the speech team was already looking a little bit into neural networks, and we felt that by helping them scale, we could help Google's speech recognition improve. And so it wound up being a little bit opportunistic based on who wanted to work with us and who we thought we could work with to drive the scale hypothesis.
That gave you a team to work with and help. It also helped you understand if you were becoming good enough to be useful, right? Because they had a very clear benchmark of what they considered hard and so what they would consider impressive in terms of progress.
Yeah, so we're fortunate that we could work on deep tech innovation, invent neural network architectures, and then also we're kind of held accountable to deliver real business results relatively quickly. So I remember work on speech, working on Google Street View, where we were at the time using computer vision to look at Street View images to read house numbers to more accurately geolocate houses in Google Maps. And that turned out at the time to be a bigger impact thing than speech recognition. Had conversations on how to help advertising. I remember in early skepticism about web search, I struggled to convince the web search team at the time. Fortunately, the advertising team was much more open to this. So,
do I remember correctly that you were also looking at YouTube videos and doing some filtering for inappropriate content?
Yes, I remember Jay Yagnick's team at the time was running AI on YouTube and did a lot of really good work on helping tag YouTube videos based on the content and also some of the moderation filtering. So there was actually a lot of because of the class that I led with about 100 Googlers or something. There was actually a lot of interest from different application teams, and we're fortunate. We're actually fortunate to have a lot more people wanting to join Google Brain even early on than we had headcount for. But sometimes if someone wanted to join us, but we just couldn't bring them in full time, we say, let's just work together, and that set up a lot of collaborations.
It was maybe just under 2 years, I think, from the day you started at X till when Google Brain graduated from X and moved to Google. What did you think on that graduation? Was this like about time, or we're being kicked out of the Garden of Eden, or something in between? Like, how did that process of moving over to Google feel? Or was it like, well, whatever, it's all just kind of Google, so it doesn't matter?
It was a little bit of all of the above, to be honest. X still is a very special place. And so I remember when I was working in the X building way back then, it was really nice that, like 10 feet from me would be at that time, chauffeur, now Waymo team, and then team working on balloons, and then also the, glass team, and just several feet from my desk were all of these teams doing all of these wild, exploratory, insanely exciting things. So, while graduating from X was presented as a graduation and the next step. And I think ultimately it wasn't a bad thing that we moved to Google core and became closer to the business and got more resources. So no regrets at all. I think it helped set us up for success. It was also a little bit bittersweet to leave behind that wildly exciting X building, which was crazy stuff happening just a few feet from where I was sitting every day.
What changed after the team moved? You stuck around at Google for another maybe year and a half after it moved?
I think so. Yeah, I think after we moved, I think it became more focused on one thing, which was neural networks and scaling. We probably spent less time hanging out with the Waymo people and getting free rides in the very early Waymo prototypes at the time. And then I think we became more, I was going to say corporate, but not at all in a bad way. I think it was helpful for the Brain team that we became much more connected to a lot more Google businesses. One thing I believe back then, I still believe now, is this technology is exciting. We should work on deep tech, but in isolation is completely useless. The value is when we find applications for it. So when we moved into the main Google building, we're physically much closer to a lot of the important application teams. So it was, a minute walk away to talk to different teams building really important applications that we could collaborate on. I wound up shifting gradually from Google Brain to running Coursera more day to day. Yeah. So I think, had started Coursera out of my machine learning class at Stanford. My co-founder Daphne and I were running it day to day. And then partly because Google Brain was going well, and I was so confident I could hand off the leadership of the team to Jeff Dean, who was a wonderful partner. I felt, whereas in contrast, I think Coursera is a very early thing, needed much more day-to-day leadership. So then I talked to Jeff, and we very gradually, over the course of like a year or something, had me hand over the reins to him. And I think that fortunately worked out well too.
Yeah, for sure. You're still on the board of Coursera, aren't you?
Yes, I'm still chairman of the board.
Congratulations.
Oh, thank you.
So I'd love to hear from you a little bit where you think AI and machine learning is going, and also sort of where you've gone afterwards, what you're doing now.
Yeah, so these days, including taking some early lessons I learned by watching you, Astro, and X operate, is spend a lot of my time running AI Fund, which is a venture studio, and we build an average of about one new startup per month. I continue to also do a lot of AI education things through democratizing and through Coursera. But I think AI is wildly exciting. Companies like Google are doing a fantastic job training foundation models. I think the latest version of Gemini really, the team really did a great job. And I'm wildly excited about the number of applications that would be built on top of these foundation models. So it feels like when I go into work every day, there are so many cool applications where I think there's clear market demand. People make people's lives better off, but just no one's gotten around to building it yet. So I find that very exciting.
You said one new startup per month. That's the rate at which they're coming out of your pipeline. Yeah. How long do they spend in your pipeline?
So about 6 months from idea to launching a startup. But about half of that time is getting up to hiring a CEO. But once you hire a CEO, they spend 3 months with us, after 3 months, with about, let's say, a 75% graduation rate, 25% we or they decide to not move forward. So basically, once the CEO is with us, 3 months, and we'll launch a startup. And I think one of the things that's changed in AI is the cost of prototyping has gone down dramatically. So, if you have an idea, it's so inexpensive now to build a prototype and then take it to users, validate or falsify it. And if it's falsified, great. You just wasted, 2 days and $5,000 or something. And this is really picking up the pace of innovation, especially in the application layer where we take AI and build applications. As opposed to the AI technology foundation model layer, which still needs these massive billion-dollar budgets and massive data center build-outs.
Yeah, I think about it as the difference between like electricity, or transistors, the sort of foundational layers of what by the end of the 20th century was sort of the computer industry, the internet infrastructure. All of that was profoundly enabling, But we also then had tens of thousands of things to build on top of that to realize the value of that. In that same way, foundation models, sort of machine learning, and these large models that are now available to everybody in the world is like the electricity. It's like the transistors. It enables an incredible number of things, but you have to go do things with it.
Yeah. In fact, if you look at the electrification of the United States and other countries, building electric power plants was a great business. Lots of people build electric power plants and they do very well. But if you look at the consumer electronics industry, or the things built using electricity, that's far bigger than the power plant industry. And I think it will be like that for AI. Building AI models will be huge. It will be massive, but it won't be nearly as massive as the collective set of things will do, building tons of applications on top.
I love your passion about artificial intelligence, and we'll come back to that one. You also have a passion for education. You mentioned Coursera. You were a professor for a while, but I'm betting that your passion for education is much bigger than the time that you spent actually teaching. Tell me about your passion for education.
I think I grew up, trained by my parents and so on to realize it's not about me. It's always about setting others up for success. And then at Stanford, I remember teaching machine learning, and I was walking into the same room, delivering the same lecture year after year, even telling the same jokes. And after a while, I asked, is this really the best use of my time in terms of setting up students to be successful? So over a span of a few years, I wound up trying to get the videos recorded and posted online free for anyone to access. Wound up prototyping things like auto-graded quizzes, learned from Sal Khan of Khan Academy that we should do shorter videos. And it turns out that before Coursera, which suddenly went viral, there were, I think, 5 other versions that you would never have heard of, some of which had like 20 users or something, but that allowed me to learn important lessons about how to build a scalable online educational platform. And when that worked out, I felt there was an opportunity to take training to a very large audience. So I invited, our staff colleague to join me, and we wound up building up Coursera from there.
And tell me about artificial intelligence and machine learning. When did you get passionate about that? How did that sort of bug start with you? At what age?
I remember it was in high school. I did an internship as an office admin, and I just remember doing so much photocopying. Not my favorite. And frankly, it was boring. And I remember as a teenager thinking, oh boy, if only there was something I could do, like some sort of automation that could do all this photocopying for me. Maybe I could do something more fun. So since a very young age, I was really excited about automation and how it can free up people's time. And I was fortunate also that my father, a doctor, at the time was actually experimenting with very rudimentary AI algorithms for medical diagnosis. So my distaste for the amount of photocopying I had to do as office admin and learning about neural networks as a teenager, I think since then I've been passionate about AI as a form of automation on steroids.
So since we started talking about this vision that you had that was at the time, literally people were getting up and yelling at you about, what do you think are some of the things coming down the pipe for us as humanity with respect to artificial intelligence and machine learning that people don't see coming clearly yet? I'm not trying to suck you into some unproductive AGI conversation, but just like, how do you think the world's going to be in, call it 10 years, that might surprise listeners?
There's one thing that I'd love to see. I feel like I'd love to see everyone learn to code, or with this new style of coding, which is much more AI assisted. And the reason is maybe in my professional life, obviously I do a lot of coding, but in my personal life, I write applications for my kids. A few weeks ago, week ago, I was writing an application to print out flashcards for my daughter to practice a multiplication table. It took me less than a day to build a new prototype that I could call up on my phone and talk to get a custom prompt and talk to me about topics. But a lot of these prototypes that used to take weeks or months to build now can be built in hours or maybe less than a day without writing that much code, because AI can write the code for you. And I think that demand for software engineering is massive. So many of us would love for so many more programs to be written, but it's just been too expensive. And I think 4 states in the United States out of 50 already require some computing education to get a high school diploma. I hope it'll be someday 50 out of 50 states, because if we can get everyone to learn how to use computers to build things, not just be users of computers, but be building alongside computers, I think every human can be much more powerful. It turns out that one of the most important skills going forward would be the ability to get computers to do what you wanted to do, because computers are becoming more and more powerful. And I feel like a world where we teach all children to code in a new way of coding will set up the next generation to be much more powerful than the current one.
And how about sort of outside the United States, maybe even outside of the sort of the larger, most developed economies? How do you think AI is going to affect the world more generally?
I feel like I hope that AI will have a very large democratizing effect. Because one of the most expensive things in today's world is intelligence. It costs a lot to get a highly skilled specialist doctor or to tell you what's going on, or costs a lot to get a highly skilled tutor to mentor your child one-on-one. And AI, and whereas I don't see a path to making human intelligence cheap, it just costs a lot to train a skilled human being. There is a path to making artificial intelligence cheap. And what this means is today, only the relatively wealthy can hire certain types of staff to do certain types of things for them. But in the future, I would love a very single person can have an army of smart, well-informed staff to do all sorts of things for us. And I think this would...
Their health advisor, their tutor, that kind of thing.
Yeah, yes. And I think that giving everyone an army of staff to help them that today is available only to the relatively wealthy, this will lift up a lot of people.
I'm really curious to hear yours definition. This is a little tongue-in-cheek, but I've always felt, as sort of a longtime practitioner, and I know you are as well, obviously, AI has traditionally been this sort of receding frontier where as things start to work and become an everyday part of our lives, we stop calling them artificial intelligence. So my favorite working definition of artificial intelligence is the things that computers do in the movies, which in a certain sense is totally unfair. But you remember that moment where computers started being better than people at chess, and all of a sudden that didn't count as intelligence anymore by definition, because computers were better than people at it. And I was like, well, okay, that's not a very useful definition of intelligence then. How would you define artificial intelligence?
Yeah, one of the things that I think has contributed to AI's success is while on one hand it sometimes feels like it's always far off, I think as a field we've been pretty embracing of whatever people want to enter our field and call AI. And so I find that just myself, if someone is doing something that makes a computer demonstrate some semblance of intelligence, if you want to call it AI, fine with me. I will agree with you. So I think the fact that we're quite embracing, if you want to call your work AI, it's okay. As opposed to too many of us going around saying, no, that's not really AI. This lets our field keep growing.
So maybe as a build on that, we would call it AI in a very general sense, to the extent if a person did something like that, we would call that behavior intelligent.
Yeah, yes, yeah. And the criticism is, very simple programs use an if statement to make simple decisions. That is intelligence. And is that really artificial intelligence? I'd be inclined to say yes. If you think it's intelligent, call it AI, I will fully support that. And I think that I find that disciplines tend to be more successful when we just embrace whatever works rather than being too defensive and saying, no, you're not one of us, you're not one of us. I think AI has avoided that.
I agree. So the culmination in a way of Google Brain's time at X was a paper that was published to quite a bit of fanfare in the New York Times about cats and cat videos. Can you tell us a little bit about what led up to the work that was featured there? What specifically was sort of being highlighted? Because this was sort of the coming out moment for Google Brain.
Yeah, when we announced Google Brain was through that, now slightly infamous Google Cat paper.
Yeah.
I remember we had this idea that to get enough data to learn from, we wanted to learn from unlabeled data. So labeled data means you had someone look at pictures and say, this is a dog, this is a cat, this is a person. Those are labels that are very labor intensive. But we want to learn from unlabeled data. And specifically, we built a very large neural network, possibly quite likely the largest in the world at that time, which would go to YouTube and just watch tons of YouTube videos and learn from pictures or from YouTube to see what I could learn from that. And I remember it was my then Stanford PhD student and Google Brain team intern, Kwok Ler, who's still here at Google and doing great work. I remember Kwok one day calling me over and say, hey, Andrew, take a look at what I have on my computer. And I walked over and he showed me this ghostly picture of a slightly fuzzy black and white cat that the algorithm had discovered all by itself by watching YouTube videos, because stereotypically a lot of cat videos on YouTube. But the fact that an algorithm, just by looking through tons of data without any human intervention to tell it there's even such a thing as a cat, had, quote, discovered this cat face by itself, that was an incredible breakthrough moment.
Yeah, exactly. You have a quote that's somewhat well known. I'd love if you'd share the quote about AI and work and sort of what's led you to believe that and how you think that humanity can sort of work best with artificial intelligence going forward.
I think every knowledge worker right now can get a significant productivity boost from AI, but AI is still far from automating everything that most people could do. And what that means is, I don't think AI will replace people, but people that use AI will replace people that don't. And I'm paraphrasing my friend Kurt Langlotz that first said this about radiologists, but more generally, today I can't imagine hiring an employee for most roles that doesn't know how to do Google search. It's just just so strange in the knowledge economy to not know how to search on Google. In the future, I think for most roles, we just won't hire anyone that doesn't know how to use AI in a really effective way.
Yeah, probably right.
But having said that, it turns out that salaries often get adjusted over some time to productivity. So AI will make people much more productive. And so I think that a lot of people will actually do much better financially, will get paid a lot more by becoming facile with AI as well.
Yeah, I agree. There's a lot to be excited about and hopeful on.
Yeah.
Any thoughts on either some fun stories of things from your time at X or takeaways for what it takes to successfully drive a moonshot?
One thing that was really precious and rare in the early days of X under you and Sebastian's leadership was the cross-fertilization of ideas. I remember one day someone from the Waymo team, they just came and said, hey, Andrew, want to ride in a driverless car? I said, sure. And then I hopped into one of the early Waymo prototypes and then drove around, downtown Mountain View in a driverless car. And I think that degree of openness and idea sharing and the willingness to just do weird things, some of which really worked out brilliantly, that's really rare and precious.
Yeah, and thank you. And I'm sure it went in both directions. You probably got inspiration and ideas from Waymo, from that ride even, but I guarantee you it went in the other direction as well. Like fast forward to today, and Waymo uses large foundation models for a lot of what they do, right? So that cross-fertilization is literally cross. It goes in both directions and helps both parties. So.
Yeah, and I really like that everyone back then, and I'm sure even now, felt like, feels like you're doing work that matters, right? You're not showing up to do some boring thing. But I remember actually Larry used to go around and ask people, if what you're doing succeeds beyond your wildest dreams, will anyone care? And the obvious implication being, go work on something that you can answer yes to. And I think that felt really good, that even back then and throughout everywhere at X, people felt like, don't ever work, but if it works, boy, a lot of people are going to care.
Yeah, exactly.
I want to share one thing I personally tend to obsess with, which is speed. Because when you're innovating, almost by definition, you don't really know what you're doing. And your ability to execute really quickly and try lots of different things is an important component, I think, to success. And what I find is that it turns out when I interview people for jobs, everyone will say they know how to move fast, but there are dramatic differences, like easily 10, maybe 100x differences between the paces with which people execute. So I've spoken with leaders that will have a 15-minute conversation and just make a decision. And I've also spoken with leaders that in a similar situation will say, great, let's study this for 3 months and we'll reconvene in 3 months. And I find that there are these dramatic differences. And part of the key to innovating is, I think, for a big company like Google, you don't want one random engineer to do something that takes down Google web search. It's just not acceptable. But I think X, for the most part, creating a safe environment, we could do whatever we wanted on Google Brain. There was no risk that I would accidentally do something to take down Google web search, because I didn't have the authority to do so anyway. That let us move really quickly and try things out. And I think that speed of execution with the sandboxing of the guardrails to make sure no one can do something crazy to take down the mothership, that combination is hard to create. And I think X managed to do that.
Thanks, Andrew. I agree. My version of that same mantra is the tightness of the learning loops. I don't care how long it takes for us to get to greatness or to figuring out that we're on the wrong track. What I care about is the length of time between hypothesis and results that we can assess. Yeah. If that takes an hour or that takes a month, like, you're in a different universe in the second case relative to the first case.
Yeah, well said. A lot of innovation is about learning, because if only we knew, we could have rebuilt the whole thing in a week. So it's about figuring out what to build and how to build it.
Exactly.
Well said.
Absolutely wonderful. Thank you for doing this with me, Andrew.
Thank you, Astro.